Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and in the top MCQ section of COMEDK Launchpad, today I am going to discuss two chapters from optics, ray optics and wave optics combined together, and some very important and interesting questions I am going to discuss with all of you. So let's start with the first question. A concave mirror of focal length f produces a real image n times the size of the object. Okay, so n times size of the object, so the magnification is n. Okay, and we know that magnification is basically given by v by u. So we see v equals to n into u. Okay, and the distance of the object from the mirror is, so you have to find the distance of the object from the mirror. So basically you are trying to find u, and mirror equation is 1 by v plus 1 by u equals to 1 by f. Now in the case of concave mirror, real image, everything is negative, so we are not considering any sign. Signs will be cancelled anyway. Now v is nu plus 1 upon u equals to 1 by f, or f equals to, or what we are trying to find? We are trying to find u, right? So let's do one thing. Let's take 1 by u common. So 1 by u common, we get 1 by n plus 1 equals to 1 by f. Okay, so u equals to f times 1 by n plus 1, or it will be f into n plus 1 divided by n. Okay, correct answer option C. Next question. So these are very interesting questions, and this type of questions is generally not seen even in JEE mains or in KSET exams. So these are completely different questions from all the other cases. A double convex lens made of material of refractive index mu1 is placed inside two liquids of refractive indices mu2 and mu3 as shown in the figure. mu2 is greater than mu1. mu2 is greater than mu1, and mu1 is greater than mu3. So mu1 is greater than mu3, but mu2 is greater than mu1. Okay, so this is the relationship. A wide parallel beam of light is incident on the lens from the, so a wide parallel beams of ray falling on the lens. Okay, the lens will give rise to a single convergent beam, two different convergent beams, two different divergent beams, a convergent and a divergent beam. So if you observe this, the focal the refractive index of the outside is more than that of the inside for the top part. Okay, so the top part lens will become a divergent lens, whereas the bottom part is a normal case. Okay, so air, this is glass, so air and glass generally give you a convergent ray. This is a convergent lens obviously, so it should give you a convergent ray, but this one will give you a divergent ray. So the top part will give you a divergent ray, the bottom part will give you a convergent ray, so you will get a convergent as well as a divergent ray. Next question. The angle of incidence for a ray of light at refracting surface of a prism is 45 degrees. The angle of prism is 60 degrees. If the ray suffers minimum deviation through the prism, the angle of minimum deviation and the refractive index. Now this question we will solve half we will guess. Okay, so what is the minimum deviation? Minimum deviation is 2I minus A. Okay, so 2 into, so here if you see that refracting incident angle is given 45 degrees, the angle of prism is 60 degrees. So 2 into 45 minus 60, that is 90 minus 60, that is 30 degrees. Okay, so angle of deviation you have calculated. Now should we need to use the formula of A plus delta by 2 divided by sin A by 2 formula to calculate refractive index? No. Why? So if you see that in the 30 degrees there are two refractive indices, one is less than 1, another is greater than 1. Okay, refractive index less than 1 is not possible, so refractive index obviously will be greater than 1 or equals to 1. Less than 1 means speed of light is greater in that medium than even vacuum, so refractive index less than 1 is not possible, so definitely the answer is 30√2. So this is how you should reduce your time. A ray of light from a denser medium strike a rarer medium, the angle of reflection is r, and that of refraction is r dash. The reflected and refracted rays make an angle of 90 degrees with each other. The critical angle of the medium is. So here we have a ray, it partly refracted and partly reflected. Okay, this angle is 90 degrees. The angle of refraction is r. Angle of refraction r means what is angle of incidence? Angle of incidence is also r. So if angle of incidence is r for this, the same angle of incidence for refraction as well, and refractive angle is r dash. So what is the refractive index of the medium? Refractive index is sine of incident angle divided by sine of refracted angle, right? Now in this case, this angle is 90 degree. This angle is 90 degree means r plus r dash is also 90 degrees. Okay, so because total angle is 180 degrees, total angle 180, and out of that this is 90, so they should be also giving you a 90 degree value. So from there we can say that, okay, let's see. Now we are trying to find the critical angle. So critical angle 1 by sine theta c, that is equals to refractive index, right? Or sine theta c equals to 1 upon mu, we know that, or this is equals to sine r dash by sine r. So that's why I waited over here which one to substitute. So r equals to 90 minus r dash. So basically you get sine r dash divided by cos r dash. So complementary angle, so you can substitute this, right? Or it is tan r dash, or theta c equals to sine inverse tan r dash. So this is the answer, sine inverse tan r dash. Next question. The given figure shows three cases of ray passing through a prism of refracting edge A. The case corresponding to minimum deviation, the minimum deviation, in case of minimum deviation, this ray is parallel to the base. Okay, so if this ray is parallel to the base, then this is the minimum deviation. So correct answer is 2. Okay, you have to remember that. So option 2 is correct. Now, a convex lens is made of 3 layers of glass of 3 different materials in the figure. Okay, we have material 1, material 2, material 3. A point object is placed on its axis. The number of images of the object is. Now because all of them are from the same way, okay, refractive index, even though refractive index are different, so because they are one after another, okay, so the final image will only be 1. Okay, so whatever image found by this one will act as object for this one, and whatever image found by this one will act as object for this one. So ray can pass through this only one way, so that is why only one image will be formed. Next is this one. A ray of light suffers minimum deviation in equilateral prism P. An additional prism Q and R of identical shape and of the same material as that of P are now combined as shown in the figure. The ray will now suffer. So here you have to understand that the ray is suffering minimum deviation. Okay, now this and this, everything is same, and we know that one equal and opposite prism basically cancels each other. So Q and R will cancel each other, so P will remain as it is, so the angle of deviation will remain the same. So it will remain the same as before. Okay, but if you add only one opposite, then there will be no minimum deviation, and if you are adding 3 of them, then these 2 prisms will cancel each other and you will get only same minimum deviation. In a laboratory, 4 convex lenses L1, L2, L3 and L4 of focal lengths 2, 4, 6 and 8 cm respectively are available. 2 of these lenses form a telescope of length 10 cm and magnifying power 4. The objective of the eye lenses are respectively. So length is 10 cm and power is 4. So length is basically FO plus FE and magnifying power is FO by FE. Okay, so now if you see that length 10 is possible in 2-3 ways. Okay, 8 plus 2 is 10, 4 plus 6 is also 10. So but if you consider the magnifying power 4, that is only possible when you are considering 2 and 8. Okay, so 2 and 8, if you take objective lens as 8 and eyepiece lens as 2, then the magnification will be 4. So definitely you will consider this as eyepiece, objective, this as eyepiece. So objective is L4 and eyepiece is L1. So correct answer is option D. 2 light waves of intensities I1 and I2 having same frequency pass through same medium at a time in the same direction and interfere. The sum of the minimum and maximum intensities is. So what is the maximum intensity? Maximum intensity is square root of I1 plus square root of I2 whole square. And what is the minimum intensity? Minimum intensity is square root of I1 minus square root of I2 whole square. Now if you remember the formula, A plus B whole square plus A minus B whole square is equals to 2 A square plus B square, right? So you will use this formula over here. So that is equals to 2 square root of I1 whole square, that is I1, plus square root of I2 whole square, that is I2. So the add of intensity is basically 2 I1 plus I2. A single slit illuminated by light of wavelength 600 angstrom. The slit width is 0.1 centimeter and the screen is placed 1 meter away. The angular position of the 10th minimum is. So we know that A sin theta equals to n lambda for diffraction minimum. Now sin theta is very small in this case. So sin theta will be equals to theta. So we can say that theta equals to n lambda by A. Now what is n? N is 9th or 10th minimum. So 10 wavelength of light is 6000 angstrom. So 6000 into 10 to the power of minus 10, and A is 0.1 centimeter. Okay, so it will be, and the distance does not matter, screen distance does not matter over here. So you will get this as another 0 you will get over here. 0.1 means multiplied by 10, so it will go 1 2 3 4 5. So 6 into 10 to the power of minus 5. Okay, this is centimeter, sorry, centimeter means I made a mistake. 0.1 centimeter, 0.1 centimeter means 0.1 into 10 to the power of minus 2. So another 2 will reduce, so you will get the in radian, this value will be 6 into 10 to the power of minus 3. 6 into 10 to the power of minus 3 radians. So correct answer is option B. Next, to observe diffraction, the size of the obstacle should be lambda by 2, where lambda is wavelength, should be the order of the wavelength. Obviously, to observe diffraction, to observe interference, the wavelength should be, gap should be of the order of wavelength. Okay. If the first minima in a Young's slit experiment occurs directly in front of one of the slits, distance between the slit and the screen is D equals to 12 centimeter, and the distance between slits D equals to 5 centimeter, then the wavelength of the light used. So here we have, this is the Young's double slit, okay, and it says that the diffraction minima is exactly occurring here. Okay, so diffraction minima is exactly occurring here. So what is the, first of all, what is the path difference? That is most important part. Okay, path difference is equals to lambda by 2. If the path difference is equals to n lambda by 2, n plus generally 2n plus 1 lambda. So for 2n plus 1 lambda by 2, for first one it will be lambda by 2. Okay, n equals to 0. So this is the formula for first minimum of Young's double slit interference. Now it is said that what is the path difference between these two? So this distance is d square plus d square, right? Pythagoras theorem, this is capital D, this is small d. So this is d square plus small d square. Okay, square root of. And what is the distance traveled by this? Distance traveled by this is equals to d. So this is the path difference. Okay, as simple as that. Now you have to put the value and calculate path difference, then you can calculate lambda. D is, capital D is 12, so 144. Small d is 5, so it will be 25 minus 12, so it will be 169 square root is 13 minus 12 is 1. So path difference is 1, and that is equals to lambda by 2. So lambda equals to 2 centimeter. So lambda is equals to 2 centimeter. Basically it is the interference of sound. Okay, not light does not have 2 centimeter wavelength. Unpolarized light beam of intensity I naught falls on a Polaroid. The intensity of the emergent light is I naught by 2. Okay, in the case of unpolarized light falling on a Polaroid, the intensity is I naught by 2. If two slits in Young's experiment 0.4 meter apart and fringe width on a screen 200 centimeter away is 2 millimeter, the wavelength of the light illuminating the slits is. Okay, so so it is given that the small d is 0.4 millimeter. Okay, that is 0.4 into 10 to the power of minus 6 meters. Okay, fringe width is 2 millimeter. Fringe width is 2 millimeter. Again 2 into 10 to the power of minus 6 meters, and distance is 200 centimeter, that is 2 into 10 to the power of minus 3 meters. Now we know that beta equals to lambda d by d. Okay, lambda is given by lambda we don't know, so lambda equals to beta into small d divided by capital D. So what is beta? Beta is 2 into 10 to the power of minus 6. Okay, small d is 0.4 into 10 to the power of minus 6 again, and capital D is 200 into 10 to the power of minus 3. Okay, you can cancel this 100. So 100 10 to the power of minus 3, it becomes 10 to the power of minus 1. So it goes up, it becomes 10 to the power of plus. So 0.4 into 10 to the power of minus 11, minus 12, and there is a plus 1 from this. So it will be 10 to the power of minus 11. So it will be millimeter is not minus 6 and centimeter is not minus 3. Millimeter is minus 3, minus 3, minus 2. Okay, no one told me that I made a mistake. It's such a same. So it will be minus 3, minus 3, minus 2. So it will be minus 8 only. Okay, because this is 100, this is minus 2, they will cancel. So it is minus 8 only, right? Minus 6 only, sorry. So minus 6 means we have to convert it into nanometers. To convert it into nanometers, we have to multiply with 1000, and then that will be 10 to the power of minus 3. So it will be 400 nanometers. So by now you have understood the answer. So correct answer option C. Now last question of the day. Two identical light waves propagating in the same direction have a phase difference delta. After they superpose, the intensity of the resulting wave will will be proportional to cos square delta by 2. Okay, you have to understand that the resultant intensity is basically 4I naught cos square delta by 2. Okay, this is the formula. So from there we can say this is cos square delta by 2. Now we have reached the end of this lecture. This was a small, brief but very interesting sets of questions. Not too many mathematical questions in this section, but I hope you enjoyed this session. We'll be back with more COMEDK Launchpad session very soon. Till then, bye.